Hi everyone, our topic for Surah is depth perception using auditory system, seeing the world through ears. We are Rajan and Nimish from Electrical Engineering 3rd year and our project facilitator is Professor Brijesh Lal from Electrical Engineering Department. Let's start by stating the problem statement we are trying to solve. Our goal is to describe a static scene to a blind person. Suppose that we want to describe a room to a person, then we should tell the person where walls or any obstacles are present in that room. Current technologies which help blind for any such assistance are like cane, in which person keeps on walking and tries to understand the scene using the feedback provided by that cane. But problem with any such technology is that person cannot understand entire scene at once and need multiple attempts to understand that place. To solve this issue, we use the fact that blinds have a very good capability to localize objects in space. That means that they can very accurately pinpoint the location in space from where sound is coming. So, if we assume that every obstacle and wall in that room are sound sources and feed that sound to blind person, he or she will be able to understand entire scene in just a single run. So we capture the image of entire scene using a stereo camera, which creates a depth map of that scene of the frontal space of the person. Using that depth map, if we could create sound signal, assuming every obstacle or wall in that room is a sound source, we would be able to achieve our goal. These are the major objectives which we aim to achieve through our project. First one is to study how humans are able to localize sound from environment. Because if we could understand this, then we can generate virtual sound and feed it via earphone to the person. Second objective is to study audio resolution capability of blind. Our eyes have very fine resolution capability, but our ears can't distinguish between two sound sources which are very close to each other. Then, using these two information, we need to create sound signals which correspond to a sound source located anywhere in space. When these signals are presented through earphone, person identifies the location of virtual sound source. Now, using information from the depth maps captured by the stereo cameras, we finally generate sound signal which describe a scene to a blind person, assuming every obstacle is a sound source. Finally, we need to do testing for these generated signals, which validate our idea that such study can be taken further to provide real-time assistance to blinds. To generate sound signals, we first studied how humans perceive sound from different locations differently. We found that sound coming from any source is distorted because of pinna and reflection from different body parts. These distortions depend on location from where sound is coming. So, even if same sound is sent from different locations, different sound reaches our brain and our brain interprets these sounds differently. Hence, there is a transfer function associated with the sound which depends on elevation and azimuth of sound source, that is, spatial coordinates of that source. As we are presenting sound from earphones, we need to incorporate all these changes in sound signals which we generate. To do this, we first tried to use model of human head and ears. But the results were not very good because all such models are approximation of human body and have very high degree of personal bias. So, we finally used CPIC database which was experimentally generated to contain transfer function data for 25 azimuth and 50 elevation coordinates. But this transfer function data does not contain information about depth of obstacles. To incorporate the effect of depth, we introduce the effect of reverberation and sound pressure level, which are major source for depth perception of humans. Using all these data and effects, sound signals were generated to localize any coordinate in frontal space. When we presented a very small duration of sound signal corresponding to a particular azimuth and elevation, subjects were not able to localize it very precisely. To solve this problem, we used reference signal. This means that instead of only giving sound of a particular location, we also provided sound signal of some other locations. To understand this, consider a 2D plane of 0 degree elevation, that is, 2D plane in front of our eyes. We have small sound pulse for each azimuth in this plane. These pulses are fed to subject ears in a continuous manner. So, we first present a pulse corresponding to -75 degree, then -70 degree, and so on till +75 degree. This complete sweep from -75 degree to +75 degree takes around 3 seconds. So subject knows the distance at which obstacle is present in this 2D space. In same manner, we made sweeps for elevation, so subject can know the distance of obstacles at each coordinate in front of him. Obviously, we will not be doing sweeps for entire value of azimuth and elevation to describe a scene to a person. Actual range depend on coordinates in depth map which needs to be described to the blind person. So finally, we read depth maps provided by stereo cameras, analyze them and generate sound signals as per need. We also need to account for difference between resolution of human eyes and ears before presenting sound to any object. Study and incorporation of resolution will be explained in later parts of the video.
To get a more practical and realistic view on the applicability of the concept, we tested some sample signals we generated on some visually impaired children at the National Association for the Blind, RK Puram. In general, the test focused on identifying the localization capabilities of the individuals with respect to azimuth, elevation, and depth. For this, we performed several tests which are described as follows. Clap test for azimuth and depth. In this test, we clapped at different azimuths and depths and made the subject to identify the source of each clap by pointing their hands in their felt direction. This is done to obtain a general idea of the localization capabilities of the subject. Azimuth sweep test. In this test, we fed a signal in the subject's ears using earphones and which consisted of a sweep from left to right at 5-degree separation with two identifiable objects at azimuths -15 degrees and 45 degrees. This was done at elevation of 0 degrees, that is the head level. Depth test. In this test, the signal consisted of sounds at azimuth 80 degrees with varying depths coming nearer to the subject. Clap test for elevation. Here we performed claps at a particular location with only varying the elevation of the claps and azimuth being kept constant. Multiple sweep with elevation changes. Here, the signal consisted of 5 sweeps alternating from left to right and then right to left. After each sweep, the elevation of the sound is increased by an angle of 11.25 degrees. This was primarily done to test the ability of the subject to distinguish changes in both elevation and azimuth simultaneously. Depth map testing. Description of the object in the depth map is as follows. Object has such a shape that the azimuth varies from -29.2 degrees to +29.2 degrees. Elevation varies from -20.1 degrees to 20.0 degrees, with depth increasing suddenly at azimuth of -15 degrees. The depth then gradually falls till azimuth of 15 degrees to a value less than original. It then increases to the original value. This was intended to check if every possible variation is still identifiable by the subject and a chaos is not felt. The tests just described were performed on 5 subjects belonging to different age groups, between 12 and 19 years. Both boys and girls were considered and also the subjects had varied levels of vision from completely blind to not blind. The observations were recorded as follows. Subject 1. Aman, youngest at 12 years. Had poor localization skills overall as obtained from the clap test itself, so the signals were not used for testing in his case. Subject 2. Chavi, 13 years and partially blind. Even she did not do very well in the test based on elevation but was fine in azimuth variation. Subject 3. Prabha, 14 years old and completely blind. Here, we obtained much better results compared to the younger children. She could identify the movement correctly along with fair sense of azimuth elevation localization. She was pretty amazed to hear the sound move and correctly trace the object's path. Another important factor to note was that she is completely blind. Subject 4. Vaishali, 16 years old and also completely blind. She too was very good in identifying and localizing the signals. This subject was a 19-year-old boy who is not blind and has a perfect vision. We repeated the tests on him to get an idea if disability in vision increased the auditory perception. It was indeed the case. as this subject could locate the direction of noise when clapped but not when artificially produced, that is, our sound signals. The results of the above observations are summarized as follows. Clap test for azimuth and depth. Everyone was able to identify the sound of clapping, which only varied in azimuth. Azimuth sweep test. Mostly everyone could identify the movement of the sound in terms of direction, but azimuth identification could be done only by older children. Also, the issue of front-back reversal was resolved with age. Depth test. The results of this test was good for everyone. Depth change was felt naturally and not only mere changes in intensity. Clap test for elevation. Except the youngest subject, everyone could identify the location of claps and their elevations. The non-blind people too failed the test. Multiple sweep with elevation changes. The blind could identify the movement of sound left to right as well as could clearly identify the change in elevation after each sweep. This was only done with those who could perform the above test satisfactorily. Depth map testing. This was a difficult one for the younger aged children. They could only identify the sweep and depth but not elevation. But elder ones could visualize the shape and also resolve between the vertical separations, whereas the normal person had no clue of the sound movement. The results can be analyzed as follows. For resolution studies, we get 5 degrees resolution in azimuth localization and 11.25 degrees in elevation localization. For age-wise analysis, there is significant improvement in auditory senses with age. Visual status. A completely blind person was seen to have tremendously better localization skills than the people with normal vision. Simultaneous localization of more than one object. This could be undertaken in a future work. So, from the mentioned results, the following conclusions can be drawn. Auditory perception of a child is seen to have strengthened with age, both in case of visually impaired and sighted people. Localization and lateralization skills of the visually impaired people are way too much better than sighted people. Even among visually impaired people, the skills are more prominently reflected in those who are completely blind compared to those with partial blindness. This clearly is an indication that this can be extended to provide real-time assistance, that is, signal for moving environments. A normal human being, that is, with normal vision, could distinguish between two different sound signals simultaneously. This ability to simultaneously distinguish between different signals is more enhanced and prominently observed in visually impaired people. This was empirically tested on the subjects above. By applying various signal processing techniques, more signals can be made to localize simultaneously. The major information in a moving setting could be used as basis to generate signals in different waveforms. So this is proof of the concept that our methodology could be extended for real-time assistance. All the signals used for testing and MATLAB scripts can be accessed from the GitHub repository for which the link has been shared. Thank you very much.